Kia ora. Thank you for joining us for the final webinar in our autumn webinar series. I'm Emily Townsend, I'm president of LCANZ, and I will be your host for today. As a reminder, we have had lots of wonderful webinars up to date. Most of the recordings of the previous sessions are already available on the website, and the final ones, including today's, will join them soon. So if you missed any, you do have the opportunity to go back and view them. A reminder as well, for the last time, that we are running a competition through this series, giving members the opportunity to win their membership. So student and individual members could win next year's membership for themselves, and corporate members have the opportunity to gift an SME supplier with a membership for FY23. To win, you will need to answer questions in a quiz, which we will be sending out soon, and we'll cover all of the sessions. So again, a reminder, if you did miss any, that some of those recordings might cover any of the gaps that you might have. With no further ado, I am delighted to welcome our speaker today, Ranvir Singh. Ranvir's Associate Professor in Environmental Hydrology and Soil Science at Massey University, and his research is focused on the development of tools and practices to assess and minimise the impact of agricultural production systems on water sources. So perfectly placed to talk to us about water footprinting of agricultural systems. And Ranvir, I will hand over to you. Welcome and thank you.
Really pleased to join you in this afternoon session to talk a little bit about the work that I have been involved. I am a agricultural, water science, soil science person. I did my master's and bachelor's in Haryana Agriculture University in India. It's one of the state quite intensive agriculture in that area, especially crops, wheat, cotton, rice. And I learned around water use in my studies in those fields, and carry on my interest on studying the water use and its assessment into agricultural crops. And I got a chance and opportunity to go and do my PhD study at the Wageningen University in Netherlands. And that's where I got introduced to more on the science around this water use assessment. And in those days, we were debating about the utility of water use indicators around like water use efficiency or water productivity that was defined around 1997 by David Molden from IMI. And so I did start working on this project with some colleagues from Netherlands on how to define water productivity using more soil water balance components, and how to calculate that water productivity by using the combination of local data, field experiments, and modeling. And that's took my interest more into this area of water use assessment. I got introduced and carrying on with my interest with the Arjen Hoekstra, who founded the Water Footprint Network. And I got involved with some of the working groups with Water Footprint Network around the methodology around water use assessment, gray water footprinting. And then I got involved more and more with doing some research projects with students, supervising their master thesis, PhD thesis like Indica, Amber, Caleb, and currently I'm supervising a PhD thesis in India for water footprinting of milk production. So what I'm going to do is, as you see, that I'm pretty much a agriculture, water use focused person. So I'm going to share some of that, my learnings and experience around this water footprinting in agricultural products. So that will be our session this afternoon. So the focus will be on agricultural products and the relevance of local data and local context, why that is important. Now you did hear from Professor Sarah McLaren and Dr. Brent Clothier on the water footprinting techniques, and Brent talked about issues around the methodological approach that we have, different approaches, including the hydrological approach. So building on that, I think I would like to highlight a little bit more a point on the role of different data sets and models to calculate and to quantify these water footprints of agricultural products. So that's we will take on. So yeah, you are welcome to ask your questions towards the end. Hopefully it will be an interesting session with some good results that I want to show you. So now one thing that I learned into this water footprinting work, being involved for last now maybe 2002 to almost 20 years now, being working on in one way or other way, that what are we trying to achieve here and how? And water footprinting applications, basically, they are aiming to describe this link between water use, commodity production, consumption, trade, and raising awareness, and finding those interlinkages between this water, food, energy kind of nexus in a way. And we want to identify those risk hotspots into our production supply systems, where our risks are, where more impacts are, and then advise the efficiency, productivity, and sustainability of those systems, how we can improve their productivity and sustainability, where we should focus, why, and this. And to do so, what we do is we make use of numbers, right? Numbers are good. They are pretty good tool. And so we quantify this water footprint or water use indicators, water productivity or these things. And because numbers can help us to quantify things, also can help us to understand those scale and quantums of those things. And that's where we use the numbers as a tool into these quantifications. In this number quantification, you probably already have heard from Sarah and Brent that there has been quite a bit of interesting debate around how do we quantify these numbers. Is the volumetric water footprint in terms of volume of water used per unit of product used is the right way to go, or do we need to include the water scarcity footprint like a LCA approach in terms of quantifying the impact? Now, in my mind, I think they are both useful numbers because they have their own meaning and they should be used in that context. Now, volumetric water footprint highlights the dependency or appropriation of water resources into a production process, and water scarcity footprint or gray water footprint reflects the environmental impact of water use into that consumption and production process. So we have probably, you all know that we have heard a lot of debate in the literature, a lot of papers came out arguing one or other. That was quite interesting time. But overall, then both sides probably, in my mind, they start realizing that there is a bit of a utility of both of these approaches, and the WFN and the LCA approach. And a LEAP program from FAO did a great job to bring together these different researchers around the world to come and kind of discuss a little bit that what's the best way to go forward to use this water use assessment by this footprinting approach. And I got a chance to work with the number of these colleagues like Aryan, Anna Marie, Stefan, and a number of us. We were in those meetings. The process ran for 3 years, did go quite a bit of discussion, sharing each other's experiences. And in that one, it was kind of agreed upon that both numbers have a role to play. We come up with this table that can help to prioritize the action where we should focus on. And in that one, you can see the number, volumetric number here, the water productivity and the water scarcity footprint here. And a combination of those two quantified can help us to understand where we should be focusing on, where the critical points are. For example, a low water productivity activity in a high water scarcity area is the top priority. A very high water productivity activity into a medium or low water scarcity area probably is not the point to focus. Of course, we don't want to improve everything, but we want to prioritize. So that's quite an interesting combination of metrics that being proposed to apply into assessing the water footprint of agricultural products. That we look on the volumetric number, put that in the context of water scarcity into those local catchments, and then see which areas are critical hotspots that we need to prioritize and focus on. So that's great. That's a good progress, and obviously there is more to discuss and more to inform this approach. As Brent was talking in his presentation, bringing the hydrological law of mass balance and quantifying those impacts in a local context of hydrology. Soil water balance is quite interesting topics to explore further. But one thing in agricultural products and systems, we do realize that direct measurement of this water use into our agricultural crops is pretty challenging. For example, a direct water use into a industrial activity, we could put a flow meter, what's coming in, what's going out. You can kind of quantify the water use. In agricultural crop system, that's pretty impossible to directly measure how much water is being consumed and used by these monitoring systems. So for that, what we do make use of models, right? So we combine the local field observations and we combine them with this soil water, crop water use models, and then quantify what are the fractions of that water that being applied to crop received from rainfall or from irrigation, and what fraction of that is being used, what fraction is being percolated through the soil profile. And we need this kind of models to quantify those things. Now, as a agriculture soil water person, agriculture hydrologist, I know that there are a number of models out there that we have been as researchers developing from 50s, 60s, 70s, that they are able to quantify this water use. But they are different in terms of their complexity, in terms of their details, that they work based upon those equations, those principles of soil physics, water balance goes into them. So what does that mean? That using different models can have a different number, a little bit different number to be generated. And that's what I want to share with you, some of those effect of using different models, effect of using different data sets, and effect of using different spatial scale or temporal scale of analysis, how that can change that number, and what we need to be careful about there, and how we can progress those things. So one of this is a case study. For example, this is Sirsa district here in northern India. That's part of was part of my PhD study in 2003, 2005. Quite intensively cropped area, wheat, rice, cotton, all about 80% area is under crop. Quite a environment, semi-arid with the distinct seasons of rainfall and dry seasons, quite low rainfall into the area. Irrigation is needed for successful crop production from the canal, from the tubal water supply. An amount of that irrigation gets applied is quite unreliable and limited. So it's not fully satisfying the crop needs, that there is not enough water for all the fields to go around in those kind of conditions. Now, if you look at context and see, if I use different models to apply to this area and calculate the water footprint of or crop water use of wheat and cotton, what I do get as numbers. So I did a run here with one of the students after my PhD, that using a model, which is FAO model crop watt, quite I would say in my terms, a simple model in terms of calculating the water balance, or this SWAP model, which is a model from Wageningen University, quite complex in terms of its soil physics and soil water balance, that how it does calculate all those evapotranspiration models and water flow in the soil profile and crop water use and crop growth and all those things. So two contrasting models a little bit, and then I combine them with the different data sets in terms of input to these models. So you can source some of these data sets from global data sets, for example, like again, FAO data sets for climate, 1971 to 2001, or the local data set that are collected into the irrigation system, because I had the data a part of my study. So I can apply this swap model, for example, on a field scale, just for a field. I can apply this one in a distributed way or the whole irrigation system for 1 year. And I did apply that in a distributed way or the whole system for 10 years. Now, by making this combination of different data sets and spatial scale analysis with different models, we would get different numbers for the water use for a crop we are simulating in this case, like wheat and rice. And here are the results of this analysis. So you can see that if we apply different combination of a model and the data sets in terms of temporal and source, local or spatial, global, then we get variation into this number as it goes from one combination to other. And you get about 18 to 20% variation into the crop yield and the evapotranspiration simulated, which results into about 11% variation into the wheat water use. And if you apply that into the drier season crop, Kharif season crop, which is cotton, you see a much big variation. This is the cotton results that by doing these different models, and you get about 44% variation into the crop water used for cotton, green and blue, depending on which model, which spatial scale, which data set we are using. So that's quite an interesting thing to see, that how much this variation can be coming out of this combination of models and data sets. So we need to be aware about that uncertainty or the variation. Now, if we apply some of this analysis, something like this, Caleb, one of our PhD students, he did a marvelous job on water footprinting of milk production, dairy farming into our New Zealand systems. He went around and collected data sets from about 100 plus farms across different regions of New Zealand into non-irrigated, like totally rain-fed or irrigated farms across Canterbury, Manawatu, in Waikato region. And then he did all this analysis for how much water is used in terms of per kilogram of fat and protein corrected milk in terms of liter. And you can see if he does that on New Zealand average, he gets about this much number. But if we go and start making that analysis to be more detailed, then in Canterbury for irrigated, it's quite high, like about 250. Manawatu irrigated is less. In the Waikato, it's non-irrigated a bit less. Manawatu non-irrigated, and then you can see Waikato non-irrigated. This should be Waikato irrigated, right? And that's a correction here. But the point is that depending on the spatial scale and how we are now analyzing these different conditions, they give us quite a different number. So aggregating everything on average here kind of hides this variability we have into those quantifications. He also did go and apply this analysis to assess the blue water scarcity footprint using the AWARE method that the LCA community applies quite commonly nowadays. That you get the volumetric water footprint, and then you multiply that with the characterization factor to highlight the relative impact of that water in terms of a global water equivalent. And you can again see that if we use a global data set of those characterization factor, which is provided by this model from the AWARE, and then you apply to this different irrigated farm system. That's how those numbers looks like. So Caleb also did go and collected quite a bit of information on our water use, water flows into this catchment, consented water and used water, the runoff in the rivers. And he attempted to quantify the localized characterization factor by using the local data. And then he applied that one, and this local data graph looks like this. So quite a remarkable difference into the numbers we can get. Now, I think if we are comparing this one analysis as such, we can still see the ranking of those areas. If you use a global data set or if you use a local data set, the ranking of those is more or less same pattern. But what happened in my experience, a lot of studies are done by a model and data combination and analysis combination here, and then another study done into France or in Germany, one study done somewhere in India, and then somebody pulls those numbers together and start comparing directly to each other. And that's not a good idea, because there is this effect of all this uncertainty by comparing those numbers from different studies in different areas by different models, and then saying one is higher than other. There is quite a bit of uncertainty into that comparison. So we had to be careful about that kind of comparisons when we do this analysis. Now, moving on, a similar approach into grey water footprinting. So I was involved into this working group with the water footprinting network, where we were debating about how to calculate the grey water footprint of different cropping systems. And we did talk about all this complexity and came up with the idea of this three-tier approach, depending on the data availability, that the tier one, a simply leaching runoff fraction approach to be used, tier two, some simplified standardized model, and tier three, where you would use very comprehensive, robust modeling techniques, intensive measurement approach of those losses of contaminant from the production system. So if you look at some a bit more example details of that, in this case, for example, from the WFN approach, grey water footprint is defined as a load that's being generated by a production system, and then how much water you will need to dilute that to keep the water quality standards. That's a simple volumetric number, but it kind of gives a significance to what's the size of the contamination load is coming from that activity. That's the meaning behind it. Now, in a tier one approach, it suggests that we can approach a fraction of what we apply as a contaminant, like the nutrient fertilizer, in this case, into a field. What fraction of that is being leached, or the surplus, like you apply the nutrient nitrogen, some of that is taken by the crop. So you applied minus what taken by crop is surplus into your system. A fraction of that could leach. And we did go about trying to quantify this alpha and beta depending on the different condition of soil and all those things. But regardless, it's a simplified approach. Now we have another example here, like tier two, kind of a standardized simple model. For example, overseer could be proposed as an example of something like that, that takes account into the nutrient flows into the farm system, and then by accounting what's coming in, what's going out, and the different processes, tells us the potential of losses of those nutrients from the farm root zone to the environment. So that's a good model. That's a model that can give us some tier two approach. But if we look carefully into our environment in terms of this nutrient runoff and leaching, and especially around, for example, a lot of my work is focused on nitrate. Now, there are a range of factors that are involved into how this nitrate is being lost from the farm system, and how it flows through the catchment and reach the receiving environment where it has impact. The impact we are trying to measure, quantify, and avoid. So it depends on the loading factors, what type of applications we are doing, how much stock we are grazing, what's the content of feed, grazing duration, all those things. And then it's get influenced by the spatial factors of these fields in terms of their soil, underlying geology, pathway it's going to take, drainage or runoff, distance to the stream, all these things. And then comes these other hydrological factors in terms of variability and attenuation processes. Now, if you look on into our catchments, like in New Zealand, we have different sources of this nutrients or contaminant that they can come. And if you focus on here, for example, on pastoral systems, we have this understanding that nutrients, they flow through runoff and through groundwater, and they take different flow pathways from these farms, fields, depending on which one we are talking, right? So nitrate predominantly goes through soil percolation, through groundwater, and then comes out into rivers and streams, or through the drainage system if we have them. Now we have a good, let's say I'd say a reasonable understanding of those flows into the farm system, and a reasonable estimate, for example, models like Overseer, to do what's the amount of nitrate potentially might be leaching from the root zone of this farm system, which is like, say, top 60 centimeter. It does account some of those balances. A simplified approach, it can be improvements a lot there, but let's say this does a good tier 2 approach. What we don't know is that when this nitrate leaching from the soil profile is going through these different flow pathways in groundwater or in drainage system, what happens to it? How much of this is really being transferred from the farm to the river depends on what happens in those flow pathways, right? Because nitrate is a reactive compound. It can be changing its forms as it goes through these flow pathways. And that's where we are doing a bit of research, quite a bit of research, not a bit, a lot of focus on trying to do some measurements beyond the root zone. We are going into these catchments in different settings of soils and underlying geology and locations in the field. And we are installing some of these measurements, what we call piezometers, like these are plastic pipes. We can install them to certain depth, about 5-6 meters, and we can sample the groundwater, shallow groundwater underneath them to see how much nitrate is there. We could also install some of these suction cups to see how much is nitrate in the 30 centimeter profile, how much is in the 60, how much is at 1 meter, how much is at 2 meter, how much is at 4 meter, 5 meter. So we are kind of changing this nitrate as it's going from the top of the surface driven by land use, and how much is that flowing through this system. So we have been installing this at number of sites. This is quite an old slide. We have more data now on this thing. 6-7 sites I'm showing here across the Manawatu catchment in lower North Highland here, around Palmerston North, Massey Dairy 1, around Payatua, Woodville, Dennywork, Shannon in the Sand Country. And we have this piezometers installed in these sites. Now, most of these sites, they have quite intensive land use, dairy, sheep and beef, a bit intensive still, dairy, cropping, dairy, all quite intensive land use activity. What they are different about is that what is the underlying geology in terms of the material, the gravels or alluvium or some other material, and what's the on top of them is the soil type. Is it a more coarse, freely draining soil, or is it silt loam that drains poorly? What are those combinations? And so we have been sending students around these sites, and they've been collecting these numbers, looking at nitrate, for example. So you see that here, this is the nitrate on a scale of 0 to 16. And you go at one of our site at Dairy 1, so it's a dairy, hardly any nitrate into groundwater, shallow groundwater at this paddock. We go to Payatua, there is nitrate. Then we go to Woodville, no nitrate. Then Dennywork, in the shallow one, we have nitrate. Deeper when we don't. And in the Sand Country, we don't have nitrate into shallow groundwater. So that's quite interesting. there should be nitrate, right? Because there is a activity going on into the catchments. But we are understanding more and more is that this is because in some places like Woodville here and in the Payatwa here, the hydrogeological settings are such that the oxygen, dissolved oxygen into the percolation water does not diffuse too much into the system. So it becomes a lack of oxygen environment, which you can see lack of oxygen in these places. And in those conditions where there is lack of oxygen and some electron donors like carbon underneath, this nitrate can be denitrified to the gaseous form as emission, predominantly dinitrogen, which is benign. So though it's leaching from the top of the soil surface, but as soon as it hits those subsurface environment, it's being transformed, it's being attenuated. And that's kind of reducing its further flow on effect into the ground and into the into the receiving environment. So that's quite interesting. How spatially variable is this? Why it happens, and all those things we are researching. So, for example, we have been doing some research in the Tararua area into Horizon's Manawatu catchment. And this is a conceptual example here. Imagine this is a site based on real data sets, Upper Gorge in here close to Palmerston North. And all this land behind is being used for dairy, sheep and beef, and a little bit of cropping. And we can estimate by making losses estimate from, for example, ores here, that about 16.2 kilogram per hectare per year is being lost from these farm systems. And that is flowing through this subsurface environment, through drainage systems, and it's coming here into the river. Now we have quite a bit of records of water quality and water flow into this catchment here in the river. We can quantify how much the load is coming into the river. And if we estimate that over about 10, 15 years, I think this is about 12 years analysis, it comes about 6.9 kilogram per hectare per year. So if I compare this 16.2 to 6.9, I can quantify that about 57% of this nitrogen is being attenuated into the system. So somewhere, all of it, somewhere it's making losses, somewhere it's not making that losses. So there is about 57% is being attenuated into the system. Now, how spatial is that? Why is that? What soils are driving it? That's kind of a research we are doing. So this is an example of going then further breaking down this catchment and doing the same attenuation factor now. 0 means no attenuation, all loss comes to the water. 1 means 100% attenuation, no loss reach to the river. And you apply this factor analysis to different subcatchments, and you can see they are quite different in terms of their attenuation capacity to deal with this nitrate. It could be as low as 0.37 or 0.29, all the way up to 0.75 into some catchments. And we have been doing quite a bit of more research into this area to prove that indeed it is a transformation of nitrate. And indeed, there are these differences because of these biogeochemical processes. And they are explained by variations into different soils and geology and flow pathways into this catchment. So that's quite a emerging area of research. We are building more and more that. But if we put this one into the context of a water footprinting analysis, and we say that this is our tier 3 approach, that we are going in this direction, what would be the effect of that? So let's say I just out of representative examples, let's say there are 2 farm systems that they are operating. One is operating on the coarse textured soils with low attenuation potential, and other one is operating on the fine textured soil with high attenuation potential. Let's say both are kind of same intensity, and so they are using about 175 kilogram of urea and about 71 of effluent nutrient load comes from effluent management. So you got this similar kind of intensity farm systems located at different hydrogeological settings. And if we apply a different tier approach to this analysis, let's say tier 1, and I just assume here 10% leaching fraction, both would leach same into our accounting exercise because it's 10% of applied. Applied is same for both. If you run this conceptual farms through overseer, you would get different numbers because one is fine textured, other one is coarse textured, and overseer does differentiate between the drainage and those things between different soils. So you would get about 34 kilograms per hectare leach from the coarse textured and 19 kilogram per hectare from the fine textured. Now, if I apply that this attenuation factor, which overseer does not account, the tier 3 approach, so tier 3 approach accounts that, and let's say that I apply a 0.3 attenuation to the low potential and 0.7 to high, then those loads will be transformed to 23 and 0.7 for this fine textured high attenuation potential. And if you put this into a graphic form, that's how those numbers will look like, right? That's the difference those farms could look like. So that's making into account the local context in terms of soil, geology, and attenuation that happens, those farm systems could look very different when you account the tier 3 approach. If you do the tier 1, they look exactly same. Tier 2, differentiate them a little bit more. So it's quite important to bring these complexities into our accounting exercise going forward, right? Similarly, if you apply different water quality standards into different catchments, which is more a water footprinting network, a grey water footprinting issue, LCA, you have your own ecotoxicity potential and those things. I have limited understanding of how they get calculated, but I assume they are all driven by the load, which I'm highlighting here. So it's quite a difference in these numbers. So what I have learned into this exercises, being involved with the different students and different projects, as Brent was saying into the last webinar, water footprints, they have local water impacts, right? So it's not like a carbon footprint that the atmosphere is shared and same. Water footprints, they have local impacts, so we need to have a relevance of the local context. We need to put these numbers into the local context to mitigate what we are trying to mitigate here. And also that the quantification of these numbers or these variables we need to quantify these water footprints, water scarcity or volumetric number or gray water, we need models. It's very difficult to estimate these things into directly into the field. So we need models which are built on those observations, those field experiments, but we need those very well calibrated and validated, robust models used with the local data sets to be more relevant and more to the ground. Now, as I shown here, that the effect of different models, data, spatial scale, and temporal scales could be quite large, as we did see into case of cotton crop into Sirsa in India, and dairy farming into here in New Zealand in terms of grey water and blue water use. So we need to be careful about drawing the comparisons between these different agricultural water footprints that are estimated by different models, different data inputs, different scales of analysis in terms of space and time. One study compared to other study, if they are using different models, we have to be careful about those comparison of those numbers and putting them together because there could be a large uncertainty involved into them. And so that highlights the importance that we need to kind of somehow standardize this methodology a bit more. I mean, as we are doing in terms of how do we quantify these numbers, what indicator we use, and more debate on that, but also standardization about the model use and the spatial scale analysis, temporal scale analysis, kind of comparisons should be made apples to apples, not apples to peers kind of situation. And I see in that note, I see a huge potential of collaboration between LCA experts and soil water scientists like myself to share each other's understanding and learnings and tools to develop more of this database and tools that can help us refine some of these estimates and hence guide our advice to reduce those impacts. And last point, of course, that clearly there is this emerging science, for example, for nitrate, that not all the lands are equal contributor to the losses. It really matters how that nitrate is flowing, what soils, geologic catchment we are dealing with, because it's quite a reactive compound. It gets transformation into different ways. And we need to build more of this science and bring it into this kind of assessment frameworks. So with that one, I think I have shared most of what I wanted to share with you guys. And happy to take some questions.
Ranvir, thank you. That was a fascinating, detailed dip into all the complexities. And I think with each of the 3 water footprint webinars that we've had, I've certainly learnt more and learnt more about what I don't know, because there's some big gaps at the moment. I thought the study with the difference in nitrate runoff on different soils was absolutely fascinating. And I was wondering I first wondered if there was any difference in productivity that was seen between the different farms, and I realized that wouldn't have been your focus, but and then whether it could longer term be used for sort of policy decisions on, well, we should only allow dairy farming on this type of soil, or and I'm sure that's going to have people cringing, but it seems like a really interesting thing to look at once we have that data.
Yeah, no, that's a good question, Emily. I think there would be difference into the productivity on different soils. That's why we have this kind of our classification system of New Zealand soils in LUC class from 1 to 8, and they have different productive capacity. But technology help us to overcome some of the limitation of these soils and water and those things in terms of fertility status. Point becomes then is that which soil types or land types, they are more productive per unit of resource use or per unit of leaching losses. And then you put that on top of that, our attenuation science into that, then we can that's the idea, is that where we can keep and do our farming, grazing farming more resilient way, and where are our critical areas into catchments, and how we can minimize that. So we have done some modeling exercise for Tararua area, for example, and we have been kind of playing with this idea of we avoid the cut and carry. We do cut and carry on the most leaky soils or less intensive land use and move our intensive land use to other areas. What does that mean to the losses? We could cut, for example, in our numbers modeling, and again, they are a bit uncertain, but up to 30% load to the river by keeping the same number of, for example, livestock into the catchment. So there is quite a room to understand these things. And linking these things also to water footprinting then also helps to guide some of this planning policy and communication side of it.
Yeah, absolutely. Some really big meaty questions there, and nice to have the opportunity to influence policy at that kind of level. Ranvir, thank you so much. As I said, that was fascinating and useful. And yeah, look forward to hearing more. Perhaps in next year's autumn webinar series, we might hear an update.
Thank you.
Thank you, Ranvir. So I also like to just say thank you to all of our fantastic speakers. We've had wonderful speakers over the series. Reminder that all of those recordings are available on the LCANZ website. And also to say that we would love to hear your feedback and preferences for future years. I think looking at the stats in terms of people attending webinars and then also watching the recordings, I think we have a greater reach through this format, which is quite exciting. I've seen up to, I think, at least 85, and we've never had more than 50 at a conference. But of course, it does mean that you don't get that in-person feel. So we would love to hear from you if you have preferences and what they are. And if you ask for both, please bear with us because it might be alternate years because there's only so much we can do. A reminder again, we will be sending out a quiz covering all of the sessions quite soon so that you have that chance to win your membership for next year. That's all from us. Thank you for attending. Thank you again to our speakers and see you next time.